Good morning, everyone. Thanks for making it to our day 2 of the event. How many people here went out last night and ate a durian? Chili crab, pepper crab, have tiger beer? You gotta do the things. Had a dumpling. So yeah, thanks for coming back. I've got our day 2 program, and then I'll have a couple of comments I'm going to make, and then we're going to kick it off with Bunnie Huang, our keynote for day 2. So yesterday, I talked a little bit about how chaotic things are getting. And so briefly, what do you do when things are chaotic? One of the strategies I mentioned is you diversify. And so if you think about diversification, you might also think of distributed as an alternative strategy, right? Instead of creating hyper-efficient, highly centralized single points of failure, so to speak. And when I mean single points of failure, I don't necessarily mean technical single point of failure. It might be a policy or a legal single point of failure. So for example, engineers over the decades have been making the internet faster and more efficient. Market forces have created CDNs. Google has invented technologies to shave milliseconds off browsing times. In the early days, resiliency was really prioritized. Does anybody do source routing anymore? Right? Nobody. You can't ICMP redirect if a site's down, right? So all these resiliency functions have been stripped out because they've either been abused or they're not efficient enough. And what we're left with are single points where, for example, let's say there's a government that wanted to look at data. There's one convenient place you can go to look at data, let's say, Google, serve them with a subpoena. We call it, in legal terminology, that's called an attractive nuisance, right? Like, it's very attractive for governments and people to go to these single points. So what I'm saying in these times, you might want to look at diversifying, have multiple hyper-efficient locations, because you can't really diversify cleanly, so the best you can do is have multiple points. The other thing you can do is you can simplify. And if you simplify your stack, simplify your business processes, your legal contracts, whatever it is, not only does it require less people, the people that are doing the work, it requires less complexity for the people to understand. It's easier for the network engineers to understand what's going on. Everything gets simpler when you simplify it. And so when you're making a decision, I would suggest when times are chaotic and moving quickly, always try to pick sort of the Occam's razor, pick the simpler choice if you can, because it will pay you multiple dividends. And one of my strategies for my little network at DEF CON is I try to move trust into hardware if I can, because I don't have a huge engineering team. I don't have a NOC staff and a SOC staff, and it's just me and one other person, right? And so, but if I can move my DNSSEC key into an HSM, a little USB HSM, well, now at least if somebody compromises my DNS server, they don't get my key. Web server, you busted my web server, you don't get my key directly. You might somehow dump the USB's memory and do a lot of magic, but that's botnets. A lot of scripts, they're not doing that, right? So I get a large amount of increased integrity for a small amount of cost. Some HSM, YubiKey HSMs are. So that's my way of trying to gain more trust. And I would suggest you try to move your root of trust or your source of truth, some people call it, move it to a more reliable location if you can, because it pays dividends and it simplifies things. If you can say, yeah, we were compromised, and management asks, well, what did they take? What secrets did they take? And you're like, it's okay, it was all in the HSM. Like, great, rebuild the server, fix the bug, but you have a lot smaller problem. Maybe you don't even have to report the incident to regulators. So how do you actually analyze then how secure that hardware is, your source of truth? And so that's why I'm really excited to have Bunnie speak. So a little bit about Bunnie, if you don't know him, he first came on my radar when he was one of the first people to reverse engineer and break the Xbox. So when the first Xbox came out, it had an incredible hardware security system, and he devised a way around it. And then he went on to sort of YouTube fame before the age of influencers, and spending a lot of time in Shenzhen, and he would record his trips to chip fabrication plants. And he really helped open the door to this next generation of people who wanted to create and fabricate in China, but didn't know the first thing about it. Right? So he was a lot of a like early gateway. And so from there, his experience has just grown and grown and grown. He's very active in an open RISC-V community. He builds his own hardware products and custom products projects for other people. And he's really focused on this root of trust and how do you trust, how do you trust in a hardware supply chain? So I'm really looking forward to hearing the story of his journey, how he got there, and the lessons he's learned along the way. So it's my pleasure to introduce you to Bunnie Huang.
Great. Good morning. How's everyone going? You all here today? I'm really pleased to be able to share with you today some of my perspectives on trust in hardware supply chains. So let's get started. So hardware supply chains are complicated, and depending upon sort of what angle you come from, you see one part of the elephant at the end of the day, and this kind of eye chart I have here is to try and remind us that it's not just one thing. Some people are like, oh yeah, I got like a phone from Samsung or Apple, and it made it through some network and it got to me. And then some other people are incredibly like obsessed with chip fab, like, oh, we're just gonna put the fab inside of our country and then we're going to be safe. And it sort of buries the story of like, well, actually, you may be making chips inside your country, but you're still sending them back out for packaging. They go to distributors, there's a gray market in the middle, goes through box build, customs, distributors, and then finally it gets to you. There's a whole lot of hands that touch your stuff along the way. So it's very complicated, it's very global, and it's also very vulnerable at the end of the day. And so there's been a lot of hype in the past about potential attacks. Like there were, obviously these very clear disclosures that there are actually hardware implants, right? And then in 2018, there was like, the big hack story from Bloomberg, whatever it is. But where's the smoking gun? People say like, is this all just kind of like, bunch of hype about nothing or whatever is going on? And the answer is actually we're kind of looking in the wrong places. The reporter kind of buried the lead when they wrote up sort of the big hack about how these things actually work. So today I wanted to share with you sort of my personal experiences, some things I've seen, some things I've experienced, some things I've heard about what hardware supply chain attacks look like in practice, where they might be going, and maybe what we can do about them at the end of the day. So let's get started. So I like to start with my first principles thing, which is always look at the money, look at the incentives, follow the money. What does the software curve look like for economic incentive? And what does the hardware curve look like for economic incentives? And you start from this, a lot of the way the actors collaborate, how things participate starts to play out. So, software, like software, malware, everything, has this kind of, on the vertical axis here, I have profitability. That's like how much money you might make per unit, per interaction with a customer, right? And this volume is like the number of customers you have. So software, on day one, the first person who comes to your website, the first thing you deploy, you're not making any money. You're actually probably losing money, right? It's actually a negative profitability curve. You have to plow in a bunch of effort to get to a certain volume to get to a need. And then you have network effects that brings you all the way up to like a very profitable business. Hardware, on the other hand, is quite different. Yes, there's a lot of upfront costs to set up the production, but at the very first customer interaction, the point where you sell hardware, you generally don't give it away. The very first time the hardware comes out, like your phone or wherever you launch it, that's the highest price you're going to get. That's your most profitable moment. You make money from the first unit you sell. There's no question of like how do you make money on hardware. You make money from the first unit that you sell. And then only from there, as competition comes in, as you have competitors, as things go on, your profitability starts to drop, right? So this is like the background of how to think, to structure a lot of, to sort of think about the landscape, the economic landscape. So malware, like all software, is a scale play, right? The things that you really, really want if you're doing vulnerability stuff is you want to break once, run everywhere, exploit, right? Those things command a huge price in the gray market. Some research I was seeing, ransomware was something on the order of $1 billion per year in terms of payouts. And software supply chain attacks tend to, the ones we hear about, the really big ones, affect orders of millions of individuals and devices, right? So this is like a scale play. We're talking about lots and lots of folks being impacted. So when the software defenders start thinking about potential attack scenarios in hardware, they think, of course you're going to go for the servers, right? Why wouldn't you not go for a breach in the head of servers and DevOps? This is what we're all dreaming for. We want to have like the root keys to the cloud, right? And we want to have the signing keys for all the websites. We want to have all sort of stuff. They would be worth bazillions of dollars on the black market. And so then this report starts to make a lot of sense. People are like, okay, this is what people are obviously looking for, right? But you go back to sort of the economic incentives. If you think about the hardware guys who are doing the things, the question is, why take the risk of developing this huge exploit chain and getting out there, getting caught, whatever it is, when there's easy money to make on the first unit you sold? So my general thesis is that the numerical majority of threat actors, there are exceptions, like some outliers, but if you just took them all in the room and had them raise their hand and say what they're doing, the numerical majority of them are too busy making money on much simpler attacks than to invest in these kind of high-end attacks at the end of the day. So a solid example of one thing that people are doing is warranty fraud. The general approach goes like, number one, discover a common manufacturing defect that someone's taking returns for because they know it's out there. Figure out how to trigger it, the error code, right? So you have a device that shows error code. Then go ahead and build a device from scrap or whatever it is that shows that error code. Go it into the shop, return this freaking phone, and then get your payday, right, at the end of the day. Now, people might be like, seems like a lot of work for maybe $1,000 in payout. Why would anyone bother doing something like this? Again, let's follow the money. Let's think about sort of like how this all works, right? So folks who are working on the assembly line, let's just take, for example, China as a reference. They may earn about $3 an hour. That would be the minimum wage. And they would be on the line doing exactly like what this lady is doing, learning how to hand place components, how to reball BGAs, how to do these kind of menial manufacturing tasks, very low value add sort of things. When they get a little more skill, a little more confident in the things they do, they can actually go and then, for example, do repair, which is a higher value added activity. And so when they go ahead and say this video here is like a little independent repair guy that you can find like hundreds of these guys on the streets of Shenzhen. You just go to them with your phone, you say it's broken, whatever it is. This guy is able to, he's reballing a BJ over here, he's putting the solder balls on the back of a part, which he's then going to go ahead and stick on the phone motherboard over there. And when he does that work, he can charge you directly at least $10 an hour. I mean, depends upon like how good they are, the position in their shop, whatever it is. But that's the minimum they'll clear, I think, at the end of the day in their shop, based upon what I've seen. And so again, you can see this. There's an economic incentive for them to go from factory to repair person. But just staring at what the guy's doing with his little soldering iron sort of distracts you a little bit from other really important details. So I got a still shot here. If you look at the guy's desk and what's going on, the keen eye will see there's at least 10 displays on that guy's desk. He's got 10 displays that he's taken out of phones that were broken or whatever it is. So you can figure, okay, the $200 a display, he's got some inventory there. He's got 8 motherboards in a little tin in the back there, right? So he's got 8 cores of mobile phones sitting on his desk. I see at least 2 batteries. He's probably got a drawer full of more or whatever it is. And so this guy's got a bunch of spare parts that he's getting, and oftentimes not any cost to himself. When he repairs a phone, he's got some spare parts. He'll go ahead and he can go ahead and do what he wants with them at the end of the day. And really, an interesting point about e-waste like this is that people effectively mine e-waste for spare parts. Like this is this I love this image here. You can notice there's like this yellow sack. Inside this yellow sack is full of old iPhone 10 generation motherboards, like literally like these 50-kilo gunny sacks they pull around. And they just pour them into a bin, and they have like this shovel they're using to go ahead and weigh them out by the kilo to go ahead and parcel them out to people who want to harvest these things for e-waste. And if you walk around through if you know where to go in the districts of Shenzhen, you'll see scenes like this all the time. There's like these people who are just like sitting around, and there's like the sacks open, and like the motherboards are just spilling out into like the hallway, and they're just sitting there with, you know, a pair of cutters or a hot air gun, whatever, just pulling the chips off of these motherboards, just sitting there drinking tea, smoking cigarettes, whatever it is. And there's a phrase that my, you know, parents used to sort of describe this concept to me, 物尽其用. Sort of like, it was used more around the dinner table, where just sort of like, you know, the Chinese people don't put anything to waste. You know, from the tail to the snout, from the ear to the hoofs, we eat the whole pig. There's nothing ever goes to waste. You have to do everything you want. It's sort of like this, kind of this attitude, this original hackerism, right? If you see, it's not just a game console, it's a computer. Wouldn't it be a waste if we just played games on it? We should just find a way to find every possible value out of the things that we have in our possession, right? So this kind of attitude pervades, that ethos pervades the ecosystem. Now, this video here on the right-hand side, for people who don't look a lot of electronic parts, every one of those little glittering bits is a silicon chip, okay? And every one of those little glittering bits probably has a new part value between 20 cents and $10, okay? Each one of those bins has about $100,000 in value of parts on the inside, minimum, I think, right? I actually, when I counted these bins sometimes inside China, and I would see them, I'd be like, Jesus, it's like a $500,000 worth of inventory sitting underneath this guy's shelf. I paid a guy once just to let me run my hands through it, to sort of Scrooge McDuck feel what it felt like to casually run your hands through like $250,000 worth of like electronics. Because you don't, I mean, on a manufacturing line, you wouldn't treat them this way, obviously, right? But the point is that the person sitting behind that desk was able to take a $3 per hour skill, and now they're sitting with a desk with $500,000 worth of potential inventory in front of them. They've taken e-waste and turned it into a gold mine for themselves, right? So these people are taking all this stuff and using what they can to its fullest. Now, with that economic perspective in mind, does it not make a little more sense about how all these things happen, right? Step one, discover a manufacturing defect. Literally, this is their job. You are a repair person, right? If you see one phone that comes up with an error code, you're like, okay, sure, fix it. See another phone with the same error code. Oh, interesting. 3, 4, 5 come along. You found a manufacturing defect that they're going to have to do warranty returns for. This is literally your job. You're paid to do this, right? Number 2, figure out how to trigger the error code. Well, they have chat groups, people trade information, they have to fix it. Oftentimes, they know how to trigger if they know how to fix it. So that's also literally part of their job description. Assemble phones from scrap parts that replicates the error. Again, I showed you the images earlier. These folks, as they repair the phones, will have accumulated the cores of phones along the way, bits and pieces, so they don't have to go ahead and buy these parts as new. This is a byproduct. These are just like, you know, the tailings of the slaughter at the end of the day of everything they do. And then they can go ahead and sort of put these all together into a phone that may or may not produce the error code at the end of the day. And then that can be returned for a brand new one through some sort of warranty fraud scheme, right? Paydays on the order of $1,000, modular fencing costs. Like the guy who's literally there doing the repair oftentimes, almost assuredly, is not the person literally doing the return exchange thing. There's some fencers along the way. But they'll, for example, put together a phone and be like, well, I thought I'd build a phone that was fully usable, but it's got this error code. And they'll just sort of post on the, and say, look, I've got this phone here, I can't do anything with it. And then some guy will come along and buy it for a few $100 and then amplify that up to $1,000 through a warranty fraud return or something. There's some fencers along the way. So literally a detailed example of this in the iPhone 6th generation, there was an error 53 error, which is kind of known. It was caused by an inability to authenticate against a secure enclave. And that technology was kind of just being rolled out at the time. They're working out the bugs in it. And so a bunch of phones were sort of showing this error code. Legitimate field failure, right? Apple was like, look, we want to have a great customer experience. Someone comes with error 53, go ahead, hand the phone back. We want to get those things. We want to see what's going on, do the failure analysis in it. Have a day. Problem is, it's super easy to induce. Like, basically, there was a couple of like just go ahead and like pull this one wire low, or do a couple little jiggle this connector, whatever it is, and you could sort of induce this failure. And the only indicator of the failure was a simple black screen with a graphic. It looked a bit like this, right? You turn on your phone, that's all it would show. You plug it in iTunes, and you'd say error 53 when you're trying to do the restore backup, right? And so what would happen is the exchanged phones that would come back, instead of containing a full load of parts, they'd pull off the Wi-Fi chip, they'd pull off like some sensors, they'd pull off like bits of the baseband, whatever it is, that sort of thing. And they would like take the battery and replace it with a lower grade battery that was just enough to power it on wherever it is. They put some extra like steel ballast inside to make sure it had the right weight. And so they would actually just return a phone that was like the bare minimum need to essentially show that screen. They would actually take the LCD cores if you had bad pixels on one. Well, guess what? The screen's all dark. You can't see the bad pixels. So they would actually take someone's screens with bad pixels, take the LED display off, put it into one of these things, so there's no bad pixels in the area, hand it back, they get a new screen in turn. They could take all those things, take as spare parts, sell them, upsell them, whatever it is at the end of the day. So it was actually a pretty reasonable payday for the folks involved. Think it doesn't scale. Think this is a one-by-one sort of like problem that you have to solve. Think again. The reports show that year, around that time, they lost billions of dollars to warranty fraud. Of course, Apple doesn't publish clear financial numbers on this, but we can see sort of signals in terms of what they had budgeted and sort of what the things came back as. So billions of dollars were lost to warranty fraud. Even today, a single sort of warranty fraud ring can clear 10 million bucks, something like this. It's economically comparable to sort of what I've seen as ransomware payouts, except it's targeted at exactly one company. It's not like all the little companies in the world that are being targeted with random ransomwares. This is one big company, and they have everyone attacking it, from a like kind of a DDoS perspective against them. So it's not a small problem. It's a big problem, and there's a lot of people who are engaged in it. It also answers a question that I've been getting surprising a lot recently. I've had a few reporters call me and say, hey, why is it that when people have their phones nicked in High Street in London, they're all powering up in one street corner in Shenzhen? This is it, right? Everyone knows it. It's no secret. This is a repair market inside Shenzhen. You can go there. It's a district. Like this building down here, it's just filled with like floor to ceiling with hundreds of those little shops I showed you. It's just those guys, like just all the way down for like a city block, right? The primary business is sort of repair, recycling, trading for phones. So if you have an old phone and you want to get good value for it, this is the place to go. You get a really high value for your phone. If you have a phone that has a broken display, you get it fixed there. Batteries replaced. I mean, I've gone there and had my phones repaired multiple times. It's a great place to do it. So it's a spare used parts trading area, very low friction, cash and table terms. And so if you nicked a phone and you want to go ahead and turn it, the first thing you do is, well, if the person didn't lock it or did something dumb with their passcode, huge payday, it doesn't end up there. Those things turn on. But as sort of like the defenses got better and better and better, if you want to go ahead and turn those phones into cash, this is where they end up at the end of the day. They power on, the person says, yep, it's blocked, whatever it is. Okay, scrap it for parts. Turn it into a new phone, whatever it is. They've gotten super, super, super sophisticated about it. They've got like machines, CNC machines now that will mill out the CPU and the baseband chips because they're cryptographically linked to each other. And so they'll take one of those phones, they'll actually just literally mill out the physical ones, and then you have a motherboard that's everything but the CPU and the baseband on it. And so if you come with a phone that's been like dunked in water and everything's screwed up on it, they just take those two chips out and stick them into the other phone's core, everything else on it, and they can fix your phone that got dropped in water, right? So they do, this is your sort of the things they sort of do with it to sort of extract some value from these parts. Excuse me, grab a little coffee here. So the perspective in mind is like, if you were to think about this from the software analogy standpoint, if fuzzing could pay out, why would you develop exploit chains, right? So, if you're just fuzzing, you're spending time and money doing stuff, and you find like a vuln, whatever, no one's going to pay for it, right? You actually have to go ahead and figure out how to weaponize it, turn it into a chain, deploy it widely before you can get a payday on it. But the analogy here is like, the first thing you do, like you found an exploit, you can get money for it, right? Why would you put any more effort in to develop it more if you get $1,000 per like vuln that you found on a fuzzing run, right? So at the end of the day, these folks are basically too busy making money to go ahead and bother doing anything more sophisticated, I would say. And then, of course, over time, they get more competition. People figure out what it is. There's more, they're flooded with these sort of frankenphones. The vendor will have countermeasures against you. Your risk of being caught goes up, and so effectively your profitability goes down over time. But the moment you find that exploit, that sort of that repair defect, you go ahead and you monetize it, right? Some other observations. There's no upside for responsible disclosure, right? When you find this sort of like, first of all, the manufacturer would know that they had, a manufacturing defect. They would, you'll have to disclose them. By the way, your phones are all failing from this. They would know this at this point in time. The knowledge is only shared within a trusted network. They don't want to actually get it out there. So it's very hard to know what these things are. You have to be in the right chat groups. And as a result, the magnitude of the actor is kind of unknowable, right? It's an informal organization. And then there are sort of like deniable specialist cells with opportunistic participation. So even though I could show you the picture of that building where we know a bunch of stuff goes on, police have raided over and over again. They can't get anyone on any one particular thing. They're fully deniable independent cells. The only people who are actually committing the crime are the fencers at the end who do the warranty exchange, and they're like 10 hops away from that, right? Sort of this kind of economics first analysis I think is really helpful. And it's these kinds of things that explain a lot of behaviors that happen in the criminal world. If you just applied a hypothetical analysis like this, say like, well, what would happen if you put tariffs of 50%, 54% on things at the end of the day, and you could only make 30% manufacturing things on a good day? What is going to drive in terms of incentives? Are you going to make people make factories to do 30% upside on making goods? No. You're going to have a bunch of smuggling rings that will make 50% smuggling things into your country at that point in time. So it's not a hard analysis to do, and the outcomes are actually tragically predictable in these sorts of things. But I think it's a very useful tool to have in your back pocket when thinking about hardware problems. So supply chains problems are everywhere, right? I had made products once upon a time, spent lots of times on the factory floor trying to figure out what problems are. This is a product I made once called the Chumby One, the little Internet of Things product. Point is it had a firmware stored on a micro SD card. It's a little IoT style device, and this is a picture of the station we had where we would like load the SD cards into this rig, and we'd like hit a button and copy all Linux and stuff into it. All of a sudden, one day, we had thousands of bad micro SD cards, and the vendor was fervently denying that they sold me anything wrong, right? And so I went into forensics mode and started tearing it apart and like kind of read out some of the internal data. I was like, you know what? Like, your OEM ID is wrong. Your serial numbers start from 0. Like, this doesn't look like your normal cards. Maybe you guys sold me a fake batch, right? I did manage to get them to go ahead and fess up to that and get me a return, but I didn't stop there. I went and took the cards, took off the top of them, and wanted to see the construction on the inside. So I took a bunch, digested them in acid, and started to look on the inside. And yeah, sure enough, the cards that were failing, the die marking on the control on the inside was the exact same die marking as the fakes I would get in the market. So I was like, okay, these guys are definitely pulling a fast one on me. But then, the takeaway is that from this thing is that the sophistication of the forged goods is quite high, right? So they're built on exactly the same machines and processes as authentic goods. It wasn't like, I found crap on the inside. They were still double die stacked, wire bonded constructions. The internals were just sort of discontinued irregular or low spec materials. But then, I couldn't stop there. I wanted to see, could I actually make one of these myself? How hard was it to do? Like, why would people do this sort of thing? So I actually went around and found some factories that would do wire bonding for me and could actually fabricate these sorts of things. And it was surprisingly easy. This image here On the left-hand side is a wire bonding machine, if you've never seen one before. Every time that machine goes back and forth, it's stitching a wire between a chip and the circuit board. That's what it's doing very, very quickly. And it has like this little computer vision system that looks at the chip and finds where it should put the wire bonds down, right? And that little board you see there that looks like a puzzle piece, that's the board with the chip that we're trying to bond. I just walked in and like hand to the guy and says, hey, can you do this? He's like, yeah, sure, like whatever it is. They stop the thing and I program the machine and they do it. So it's not incredibly hard to do this. The thing is like I had the impression this was very expensive, right? Like if I quoted this out through, I don't know, one of the big packaging houses, the OSATs, they'd be like, oh, $10,000 to $100,000 minimum, you gotta have $100,000 volume, it's not possible, right? But when people have wire bonding machines and they have an incentive to work with you, you can just kind of walk in, hand them a small run, they'll do it, and you can actually fabricate things that look like the full production variant on these particular machines with single unit volumes at the end of the day. Sorry? This here? Oh, sort of cup of tea sitting around with the owner, and then I paid him just the time. It was just, the $10, something like this for like several boards. It wasn't, a lot of the trick in Asia is just make a good relationship with a guy, treat them like humans, respect what they're doing, and they'll talk to you, right? It goes a long way, surprisingly, as opposed to trying to go with contracts and lawyers, right? But that's kind of one of the tricks to sort of getting through a lot of this stuff is press the flesh and talk to people. Another example is relabeled production parts. So this happened to me. I was buying these FPGAs. They're like $30 a piece. I did a production run. 3% was failing. I binned them to the side, looked at them later on. The 3% they were failing had this little, I don't know if you can see over here, this white rectangle engraved on them. Underneath that white rectangle were the words ES for engineering sample. These were free samples that were not production rated. They're meant to be scrapped. And so what happened is that someone had gone ahead and lasered off those marks and blended them into the supply chain at a rate of about 3%, hoping that we wouldn't notice. So this type of thing passes the wetware string comp test. I had a thing where I said, read the label, make sure the part number matches. But because there isn't a wetware character for blanks and engraving, it passed. So even though that thing was there, it got around the very simple test that we were using to check this. The only reason I caught it later on because I was actually doing a silicon ID with a JTAG code to read it out and had a different silicon ID. So the takeaway from this is that hardware threats are dynamic and local. So we observe a 3% insertion rate. And so distributors make about 5% on these kinds of deals. So they actually sort of increased their profits by like 60% at the end of the day. So they went from like, a 5% to an 8% take. So they had incentive to do it. And it's always like, they didn't modify every single lot. So it's a dynamic threat and it's highly localized. So not every chip in every lot is modified, which puts the advantage on the red team side, right? So I have to check 100% of the chips on every single lot all the time to try and catch these very, very kind of rare exploits. And this is just a simple economic exploit, right, at the end of the day. In addition, there's also like total fakes. This is an example once of a 5-cent chip in a $5 package that we got in distribution. These don't last long because they're so obviously, like they don't even work. They don't even turn on when you put them in, so they get caught pretty quick. But when people talk about sort of fake versus real, it's a spectrum at the end of the day. It's not sort of like, is something totally fake, is something totally genuine. What you have here in the lower left-hand corner, so this the two axes here, on the horizontal axis, it's made with real processes and real machines. On the vertical axis it's made with real parts or fake parts, right? So on the lower left is total fake, like everything's fake, right? And there's clones and copies, and they're sort of in the lower half. And then kind of on this vertical diagonal axis are the frankenphones, right? So those are somewhat made out of real stuff. The case is real, parts of the boards are real, right? And so it's harder to tell. And then on the top right-hand side, you have like relabeled parts. So the relabeled parts, the Xilinx parts I got, those are genuine Xilinx silicon that were just relabeled, made on a real process with real designs, right? So that's very close to a genuine part. And there's a practice called ghost shifting, which there's an image here. This is taken at like 2 a.m. in the streets of Shenzhen with my camera. And what happens is the workers will come in after the plant is shut down. So the machines are set up, the tests are all there, everything's running. They come in with their own sheet metal and they're just stamping out USB connectors, right? So they're just going in, they come in at 2 a.m., power on the line and just stamp out the connectors. These guys getting paid minimum wage because a walk off with, and I don't know if you can see it here, these things are stacks and stacks. Each of those reels have like 10,000 USB connections on the inside. They can walk out with those, and just the machines are running. They do, like whatever. Are those things fake? Well, they're built on the same line with the same tests, with the same materials, just like their boss didn't get a cut of it, and the workers are walking out with something else. And a lot of times they will cut some sort of like corner to try and increase their profit. That's the risk of buying these things. But again, the point is, things happen on a spectrum. Is this fake? Is this real? It's very hard to sort of say at the end of the day. So meta observations. Hardware supply chain is an incremental cat and mouse game. It builds both the red team and the blue team's capabilities. As Apple finds ways to sort of clamp down on warranty fraud, people figure out more and more clever ways to get around it. They're to the point now where they're able to sort of mill into chips and hit bond wires to go ahead and flip bits onto chip for JTAG and whatever it is. And the adversary is much more diffuse than just an APT or something like this. The skills transfer between different cells. They replicate across geopolitical borders. You shut it down in one area, it shows up in Vietnam, it shows up in Africa, it shows whatever it is. It's kind of out there. It's hard to say actually how prevalent this is. And this here is sort of like an example of sort of how the red team, blue team dynamic works. This was the actual tap I put in the Microsoft Xbox to pull out the cryptographic keys on the inside. Because at the time when they designed the Microsoft Xbox, they thought that putting clear text keys across a high-speed bus would be secure. That was sort of like the blue team's thought. And then here the red team comes and figures out $150 board, you put it on the inside, you can pull it out, right? So this is an example of how that knowledge is now out there, and now everyone has this knowledge. The state of the art has moved forward at the end of the day. So is that the whole story? Is that like, so hardware is going to be just one-offs and software is going to be these, advanced exploit chains? At the end of the day, incentives matter. So at some point in time, the incentives cross over. It goes from favoring sort of small-scale attacks to sort of large-scale plays, right? And so the concern is that we have a large latent pool of supply chain talent. What happens if people stop deciding they're too busy making money and they have to put more effort in to do more sophisticated supply chain attacks at the end of the day? And so some of the factors that might change the playing ground is like, if they get really good at countermeasures, then it's not going to be as profitable to do like one-off fraud, right? So then you're going to have to start developing more and more complicated exploit chains. Or macroeconomic concerns, just economic variability can drive portions forward. Or an APT could go ahead and like just tilt the scales a little bit in a particular direction. Who knows? There's a bunch of things that can happen. So I want to go ahead and just briefly pivot onto the topic of what happens when supply chain attackers start to go for the chips. So they stop just being so busy making money doing warranty fraud, they actually go at the chips. Chips are complicated, and so in order to explain this, I use an analogy where I say, like, let's think about chips and compare them to the problem of what's going on inside my food. They have a bunch of similarities in terms of analogies. Some limitation analogy, a modified chip in the right server can impact millions of users. A poisoned fruit will only impact the person who ate the fruit. The remedies, for this is, $1 billion fabs for the chips. Let's put it in our country. Fruit trees you can grow in your backyard, right? If you have a backyard. But both require global supply chains, and we verify our chips about as much as we verify fruit. Very, very quickly talk through this. I'm just going to kind of rank these different threats by level of detection. So level 0 would be the easy ones, and then kind of like $1,000 to $10,000, $100,000 and up, and very hard to detect at the end of the day. So level 0 sort of things is the things we talked about. So these relabeling problems, right? So the example in the fruit analogy is like you have a piece of fruit, the vendor sees a worm ate into it, they stick the pricing label over the entry point for the worm, and now you buy the fruit, you think it's good, and when you get home, you pull the label off, and you're like, oh, this is actually bad fruit. This is just a relabeling problem. You could have caught it. The problem is no one's checking, and so these things kind of happen at the end of the day. This is the easy one. Level 1 would be sort of, if you had $1,000 to $10,000 tools, you could find it. So the example I like to use of this is like a modified network interface chip. And the analogy to this on the fruit supply chain is that someone's gone ahead and buried a foreign object in your fruit, like a razor blade or like a needle or something like this. You can detect it with a magnetometer very easily. Of course, still no one checks for it, but that would be sort of the, the analogy of the threat vector. And the idea here is like you could have a modified network interface chip. So this is a block diagram for a very, very common PCI network interface chip. This is the actual block diagram for it, and the idea is we go ahead and throw a Trojan on the inside. The Trojan would be something that was like, looked at the packets, if it saw an ICOM packet come in with a special key on it, would go ahead and just replay in the response to the last few network packets that we saw. So it's a way to get data out of a network center, let's just say. The observation I have is that everything in this diagram over here exists right now in free open source IP blocks. So I don't have to design any of these blocks right now. I can just go to GitHub repos and put it together. It's built in an older process node, something like 65 nanometers. So me, just little old me, could probably mount this attack for about $300,000. Like without sort of fab relationships, whatever it is, that's the kind of the barrier for me doing it. And if I did this, I could probably actually sell the chips for a profit. Honestly, I would probably make that money back. I'd be like, hey, look, I'm gonna sell you the super secure network chip. Like, don't look on the inside, whatever it is. You should buy this thing, it has all these features, whatever. No one's looking at the end of the day, even though these things are relatively easy to check. How big are these blocks? Just to give you an intuition of what silicon looks like. This is a micrograph I made of a chip in 65 nanometer node. The vertical axis here is 3.8 millimeters. That larger red box there is a small CPU core. So that's, if we stuck an extra one of those on the chip, you would see that thing. It's pretty obvious with a simple micrograph. This is a relatively low-end tool to do this. And a few kilobytes of RAM is that smaller corner over there. So this is why I say it's like a level 1 threat, because if you just looked, you would still see it on the chip, even though it seems kind of tricky. Level 2 threats, in the food supply chain analogy, it would be if someone laced your apple with strychnine. Strychnine is a poison that's tasteless, odorless. You can't detect it with any sort of normal means. The idea here is that now if you eat the fruit, you of course get very, very sick, but you would need like a chromatograph or some fancier lab machine to go ahead and detect this. $10,000 to $100,000 tool range. The example I have of this is a modified CPU pipeline. So, let's imagine we have a RISC-V CPU, and another assumption I always make is that you have two versions of this in the field. There's a good one, there's a bad one. There's a whole other research topic for bad by design, like what happens if there's only one version out there and there's literally a malicious backdoor on the inside that's not exactly the same as a supply chain attack. But the actual nature of the attack is that, we have an observation that on RISC-V, X1, the RA register, is the link register, right? That's what you use to go ahead and return from a subroutine call. Compiled code pretty much only uses it with a few instruction combinations, right? We can use this maybe as a primitive to do a bypass of memory protection. The way it goes is when you see a load instruction using RA as the address load, you say, oh, well, that's kind of unusual. Instead of just going through the usual physical memory translation, the virtual memory translation just uses a direct physical address. So let's strip out all the page tables and just do a fetch directly with the address, right? You can protect that with a knock sequence, so you can have like a little no-op sequence that kind of doesn't make any sense. If you see that instruction first, and then you sort of see this load instruction after it, go ahead and unlock the exploit to go ahead, and this will go ahead and sort of defeat fuzzers that are looking for this instruction set. The point is, for an example like this, I estimate it's about 10 to 100 logic cells inside of a large CPU block to put this exploit out there, right? So all the details I put there to try and give sort of like some notion of credibility to it, but the high bit is it's a relatively small amount of gates to make this happen. What does 10 to 100 logic cells look like? Again, this is a 65 nanometer CPU, so it's relatively old, but it's you see these kind of like little black dots. Each one of those black dots is like a cluster of gates around a timing element, and they form a circle around it because they all want to be equidistant from the timing element. So you have a bunch of these things that sort of mimic the timing pattern inside of a chip. One of those clusters could hold maybe about 100 gates, in the best case. And so you would be looking for a change in the order of like one of these little black dots. It gets a little bit harder to detect, but it may be detectable with a good microscope, right? And then let's talk finally about sort of what a level 3 threat looks like. This would be in the fruit supply chain analogy. Let's just say I've got an apple. It's been genetically modified to express an antibody that only attacks individuals who have an antigen that matches the antibody. So most people can eat it, but people of a certain genetic profile will die if they eat it, right? This is a very advanced sort of stuff. How would you detect it except for sequencing the genome of the apple, right? Very hypothetical, theoretical kind of thing, but we could imagine it happens, right? The analogy of this in the hardware world would be like a reduced round cryptography through a small mask edit. So people here are familiar with AES, it's block cipher, goes through multiple rounds. When we build AES in hardware, we don't literally build all n rounds in hardware. We use a single element and we repeatedly flow the data through on every single round. So the way it sort of works in the hardware standpoint is that you have an input, the data gets loaded into a register, you go ahead and you like circulate it through the hardware multiple times each round, say 14 rounds for AES, whatever it is, and there's a counter that's counting up on the side. So here on the left-hand side is the counter state, and that's what's happening with the encryption, decryption logic. And then finally, on the last round, we read out the value. The attack on this, the question is, what if you tied the upper bits of the holding registers together? So instead of counting up, the top 3 bits all moved as 0 or 1 at the same time. So you imagine it's a relatively easy thing to do in hardware, but what would be the impact of it on the cryptography? Well, if you play it out, it turns out what it does is load, round, round, hold, load, round, round, hold, load, round, round, hold. So effectively, you've taken a 14-round cipher and turned it into a 2-round cipher, right? But significantly, the timing side channel is the same. It still acts like it did all of the cycles. The power side channels are very similar. It's actually doing round functions in the dummy rounds in the middle, right? So at the end of the day, this type of attack, right, would be very hard to detect because if you built an enclave, a cryptographic enclave to the gold standard, you're generating the keys on the inside, so you don't have access to the keys. The only way you can test if it worked is to encrypt the block and then decrypt it with the same thing. Both in reduced round, it passes, right? You say, okay, well, let's look at the side channels. Side channels are the same. You can't tell what's going on the inside. Okay, what tools do I have to go ahead and look at this? You're just gonna have to cryptanalyze that under the assumption you have a reduced round variant and do some sort of differential cryptanalysis to see if this is going on. If you built this with the real gold standard stuff, where you say like, no scan chain, no inspectability, we're gonna lock it up on the inside, you don't know if this has happened or not inside of your hardware block. And this type of attack can happen with just a single via edit inside of an incredibly complicated chip. So this is a cross-section of a chip here, and that little arrow is pointing to, like that tiny little plug, you remove one of those and one of the intermediate layers, and you can sort of pull off this attack, implement this attack almost exactly, right? So this is extremely hard to detect, but devastating to a crypto system. This type of attack, we have no known mass deployable, non-destructive method for detection at the end of the day. So there's no difference by images by the attacker's designs, modifications solely on mid-level meta layers. And if you're a hardware guy like me and says, yeah, look for like a few via changes inside of a block inside of this chip, we're like, okay, it's hard enough to get those vias to image anyways. If it's missing, that might be my fault. I can't say for sure if it's like an attacker or whatnot. So we don't actually have a lot of good solutions. And the thing is, it's actually the only way we can see the vias right now on the lower end process is it's destructive. So I can sample one thing, say this is good, but the attacker could go ahead and just roll the dice and say 1 in 10,000 of these units that are going in your server farm has this exploit on the inside. And then we're not going to find it at the end of the day. So kind of the threat model recap I put out there for what could happen if people were to attack chips is, sorted by these different scenarios, levels 0, 1, 2, and 3. Generally speaking, level 0 is routinely practiced. Factories will have some things that go ahead and will check the labels of chips and that sort of stuff. Level 1 is practiced by targeted industries. So people who think they're under attack or know they're under attack will do kind of level 1 X-ray level checks on boards. Level 2, we have some academic papers on, and level 3, we don't know. We don't know how to fix these threats right now. The thing is, in practice, to a first order, no one is actually checking. We only do the label checks right now. That's the standard for checking for these errors, right? The funny part is that companies that do more checking, they won't admit to doing it, right? I've been at conferences and I'll say like, wow, you have a really big contingent of people coming from your cloud service to this hardware security thing. Why did you send so many people to here to look for stuff? Like, nah, no reason. We have no problems. Like, that's a lot of funding to have all these equipment. If we said that we had a problem and these guys said they didn't, everyone's going to go to that cloud service. We have no problems, right? So to a first order, no one admits that they have a problem, so that we don't even know what the problems are at the end of the day. And then as a result, the threat actors generally have a broad latitude to operate without any consequence. So that's maybe the other half of the reason why we don't have the smoking gun for the big hack is because the people who have the smoking guns don't want to admit there was even a crime in the first place. Now, question is, what can we do? Can we do better? My argument is we can do better, right? So my current topic of research, one thing I've been looking at quite a bit, is the infrared in situ verification of silicon. Excuse me. It's a method for inspecting certain types of chips after they've been attached to a circuit board without damage to the system. So we're not doing sample-based testing, we're not destroying the thing, we're looking at directly. This little GIF here sort of summarizes the whole loop. This is you'll see it starts with a circuit board. The loop starts here. It's a circuit board in regular lighting. That sort of reddish hue is the infrared light turning on. Change the focus, you can kind of see the details of the chip shining out from underneath. And that image, that grayscale image, is sort of like an example of the resolution we can get looking at these types of chips. So there are techniques available that we can use to go ahead and look at these things. It's just that people don't do them. And that's a topic of research that I want to look at. I'm not going to go into it because we're almost out of time in this talk, but the high bit is that you can try it at home. A very, very big part of me doing this is to open source it, make sure everyone here in this room knows that when these threats come along, we have countermeasures to them. For about a $400 DIY at-home setup, you can catch kind of levels 0 to 2, maybe not level 3, if you had the original design source to compare against. This is an example of a chip from a Apple motherboard that, looking through it, you can see it's like transparent at the end of the day to infrared light. And the whole trick works on the fact that silicon is transparent to infrared light. You can go to this QR code here. There's a link tree that has all the details of how to do this, papers, whatever it is. I'm not going to go into it, but I think the short answer is we can do better. So, recap of the talk. Supply chain is under attack, just not in necessarily an InfoSec forward fashion, right? A lot of us would naturally assume that hardware attackers would go for the private keys inside servers, whatever it is, but it turns out it's much more mundane than that. A lot of it's just plain old fraud. But the point is that as they're doing this, they're developing a lot of capability. These people are very capable actors. They can do really sophisticated hardware attacks. And then the question is, are these plays, is it just a matter of time until they pivot into more information security related attacks, right? What are the factors that can put us from a tipping point of just sort of warranty fraud into sort of these chip level attacks? Things to think about, when you're delivering this scenario is like, when does the profit to risk ratio tip such it makes sense for things to catch up? So a natural thing that is probably going to happen is that chips are a boom bust industry, right? People are like, oh, we have to have fabs in our country. We're building all these fabs. What happens when chip demand drops off, right? You now have an enormous number of fabs that are located in different countries that are going empty. What happens is the economic barriers to make chips drop. And so therefore, you have this change in the energetic landscape of how much effort it is to go ahead and start getting into chip level sort of exploits, these kinds of issues. And then there's questions like, what roles would APTs in hybrid warfare play, right? Could state level actors figure out how to synergize with this existing ecosystem of people out there? So never underestimate the power of a USB drive slipped into the hands of the right actor by someone, right? It's very, there's a potential that someone can just basically say, like, if you only did this to this particular thing, then yeah, maybe there could be some profit there. That's the kind of the sort of the dark horse question at the end of the day. And finally, not all is lost. Defenses are possible against this sort of thing, but generally undeveloped, right? So to a first order, we don't check chips at all, but techniques that are in development, like Iris, can go ahead and raise the bar to allow us to look at this. But I'll emphasize, there is no magic bullet in this industry. There's no like, oh, just hash and sign and all firmware exploits are gone. That's not a thing that we have. It requires a full stack collaboration. The device manufacturers have to be willing to make the devices to be inspected. So that's a really huge step first. I mean, even just trying to get people to be open source about anything is very hard. So open source hardware is one of the first steps of that. But then also getting like what it should look like for reference comparison, getting to use the right package for inspectability, and then finally getting the inspection tools into the hands of end users would be the last step of that full stack adventure to try and get this to work. And that's it. That's my talk on some perspectives on trust and hardware supply chains. And yep, I think we're out of time, so no questions.